Okay, guys, good morning. Welcome back again. Sorry I'm getting the stream going just right up until close to the class time, but not to worry, here we are. And just take a minute and we'll be all set. Feel free to say hi if you're here in this live stream. And in just a minute here, we will get underway. Hi there, Sebastian, Naaman. How are you guys doing? Hi, everybody. Awesome. Okay, well, it's 10 o'clock. Welcome back, everyone. All right, so today the plan is to just follow our lecture series. We have another important topic to start with. We're transitioning to a new topic in the semester. So first of all, I'll try to just review some of the stuff we covered last week on Thursday. And after I summarize those things, we'll start talking about time and the work of Albert Einstein here. Your second essay will be due in week 14, and that's going to be on May 6th, Thursday. My plan is to assign that and distribute the prompts later in the week or maybe over the weekend. There's one more topic that has to do with that paper that we will be discussing in the next weeks. So I don't want to give you the prompts too early so that you can consider the third option for a third possible prompt. But anyway, yeah, I will be distributing the prompts in the next week or so, and then we'll be on to the second paper of the class. But all right, as usual, thanks for being here, guys. I appreciate it, and make sure to keep attending, checking in, and leave your comment behind for your attendance record. So let me try to recap the work of René Descartes. Last time when we were here, we were going through the material by René Descartes. He wrote a book in 1641 called The Meditations. And so this philosopher was trying to set forth on a particular goal. By writing this book, he was trying to determine what? Can anybody tell me what was the goal behind writing the Meditations for Descartes? Why did he write that book? Hey, Justin. But yeah, that's the first question to just kind of get your minds back on topic. So why do you think Descartes wrote the Meditations again? Hey, Christian, good to see you. Let me know. And that'll be the starting point for our discussion here. Yeah, just let me know. Why did he write the Meditations? René Descartes, French philosopher of the 17th century. He wrote it for a certain reason. Someone will have that memory or the notes and will tell us why. Why did he write it? Just for fun? What was the reason? No big rush, but do try to say something. Okay. Hi, Ketan. Ketan, why did Descartes write the Meditations? To establish a sound foundation for our growing body of knowledge. Yes, very good, Naaman, you got it. So in that century, 1600s, no, it's not to show God's existence, Leo, come on. Kobe, looking for something that can work as the base stones, yes. So it's not to prove God exists, Leo, come on, that's a whole different topic. So what Descartes was trying to do was to find something that was absolutely certain, because he sees human knowledge growing by leaps and bounds. And he thinks that if you compare it to the structure of a building, it has to be set on a solid foundation, because otherwise the knowledge that we're developing will have to later on be rejected if we discover that what it was founded on was false. So he says, let's find something totally certain that we can place as these foundations for knowledge. So he's trying to find something certain. To do that, he says, use the method of doubt. Now that's my next little recap question. What's the method of doubt? How does he say to determine certainty? So according to the method of doubt, we should assume what? Assume what? What is the method of doubt? It says to assume something if something. So what is that? Just getting into the review. Hi guys, good to see everyone. Question, what's the method of doubt by Descartes? And I'm asking this because it follows from the first question. That's the way he says we'll determine certainty, but how does it work? How does the method of doubt go? Assume to be what? Assume to be false anything that can possibly be doubted. Correct. Yes, very good. So with the method of doubt, we will set aside and consider to be false anything and everything that could even conceivably be doubted. So if it's possible to doubt something, even if it's not very likely that it's false, even if it's a very unlikely chance that it's false, we will go ahead and presume that it is false. Yes, that anything should be false if it can be doubted. And he thinks that if we use this method, then it will expose, by means of elimination, those things that can't be doubted. We'll discard all the things that are capable of being doubted, and whatever's left over after that will be the certainty that we're trying to find. So first of all, he says, with the method of doubt, we can rule out everything that we've perceived by the five senses. Everything that we learn from sense perception is capable of being doubted. Why? Because it's possible that those things are perceived within a dream state. So the five senses are sight, taste, touch, hearing, and smell. Look at all the things that you can see right now, the things you can hear, smell, etc. According to the method of doubt, we could consider these all to be false if, for example, you were dreaming the whole time. So maybe even right now you're dreaming, therefore we can't say that anything that you're perceiving or have perceived is absolutely certain. So we thus now don't have certainty about all the things perceived through the senses because of the dreams that we could be having instead of having real perception. So after that, he says, what about math and geometry and stuff? Maybe that is more certain because at least there, it doesn't really matter whether you're awake or not. It's just the concept of 2 + 2 = 4. That would seem to be true in any case, whether you're asleep or not. But he says even there's room for doubt because it's possible that a being like God, well, he quickly corrects himself. He says, okay, God could do anything. He could mess up your beliefs about math, but he wouldn't because he's too perfectly good for that. So maybe there could be an evil demon or something like this that's deceiving you about all those things. And so even there, possibly maybe you've got wrong beliefs. So at the end of meditation 1, he says, there's so many things that we can doubt based on this method. Wonder if there's anything that we can be certain of. With meditation 2 then, the second chapter, he starts off and he says, actually, there's one thing that I can say is certain. Now, who knows or remembers what that one certain thing is that Descartes said we can all, well, I don't know if I should say we because that's plural, but you know one thing for certain. And what is this one thing that he says you know and you can't doubt? I think therefore I am. Correct, yes. So in more full stated terms, what he's saying is you know you exist. And how come? Because here you are thinking. I mean, you're thinking, so on the simple basis that you have thoughts at all, you know you exist. So even if you're in the middle of a big dream where you're having right now, and I don't exist, and Peachy doesn't exist, and nothing else exists, but you're just dreaming it all. Even if that was the case, then still you're the one having a dream. So at a minimum, you know you're something dreaming, and therefore you're a thinking thing, even if you don't know, for example, that you have a body or that anything you perceive with the senses is correct. So there we have it. Something remains certain despite the method of doubt. It's the knowledge the individual has of their own individual existence. And it's not the knowledge that other people exist because they are perceived by your senses. It's not the knowledge that the familiar events and objects in the world exist because, again, it's all based on sense perception. But one thing remains totally dead certain, and that is the knowledge that you have of your own existence, if not as a body, then at the least as a disembodied mind or spirit. Okay, now we're going to continue through our semester here, and we have more topics to talk about. There's more stuff that I could say to you about Descartes' meditations. There's an interesting conversation he has after that about what it is that you know for certain about yourself. And he says, well, you really only know the most essential things. Even when it comes to the knowledge that we have of physical objects, he says that that is known more essentially by the mind than with the five senses. He talks about how if you had a piece of wax and the wax was initially like solid, blue in color, smells like flowers, tastes like honey because it's made out of beeswax, then if you exposed it to a high flame, it would lose all those qualities, but it would still be the same piece of wax. So he says the non-essential qualities of it are the things that you perceive with the five senses. They're non-essential because those qualities could be destroyed, but the wax remains. And so the essential qualities of the wax are the things that it retains across time as it has been heated by the flame. And so the things that it has in common from before and after exposure to the flame are just that it's extended in space, it takes up space, that it's changeable, meaning that it's capable of undergoing changes or alterations, and that it's flexible, meaning that it can be reconfigured into different physical configurations. And he says those are the three main things that you know about physical objects, but they're understood through the power of the mind rather than the five senses. But anyway, we can move on. And we'll come back to Descartes later, so we'll talk more about him in a few weeks. So not to put him away forever, we'll come back to him. But for now, anyway, we are going to switch to another subject of our semester. So as I said a couple times in the class, philosophy is a field of study which has many different subtopics and specializations. And we've covered a few of them already so far. So there's philosophy of religion, which we started on, all kinds of arguments to try to determine whether God exists. And then there's ethics, which is the world of morality and right and wrong, good and bad. We talked about utilitarian and Kantian ethics there. Sorry. Peachy's trying to block one of you guys, so I'm going to make sure I turn the phone off for now. Yeah, so ethics, Kantianism, utilitarianism, the application of ethics to economic inequality, and then the trolley problem. And now we've just wrapped up our whole series of meetings on epistemology, which is about knowledge and what it takes to have knowledge, what knowledge is. So then we continue with another topic now, and the new topic that we're going to focus on is metaphysics. So metaphysics, guys. Let me put the word up here and explain. Metaphysics. So what metaphysics is like a deep investigation into the nature of reality and what exists. Okay. Okay, so when we just try to branch out into a focused, deep, concentrated effort to investigate the nature of reality, what exists in the universe, what is the nature of the things that exist, those type of questions are found in what's called metaphysics. Metaphysics was originally a term phrased by the ancient Greek philosopher Aristotle, and in his usage, it just kind of meant stuff that goes beyond what we know from physics and science, to go beyond the physical. But in the centuries since then, it's kind of taken on a slightly different meaning, which is the meaning you see here. Just a kind of deep and focused investigation into some aspects of reality or what exists in this reality. So metaphysical inquiry can take a number of different topics as its subject matter. Sometimes people are interested in the question of human free will. Do we have free will? Or are we just determined to act in the way that we do? Like, are we just governed by the physical forces of the universe and therefore incapable of doing otherwise than what we actually do? Some people think that we have that human free will. Other people think that it's just an illusion. Another topic of metaphysical inquiry could be, how does an object remain self-identical across time? For example, if you look at a photo of yourself from 10 years ago, you look at yourself and you're a young person, a small child, right? And compared to now, you're a whole different size, weight. In fact, if you've heard this before, every cell in your body has been completely exchanged over like a 7-year span of time. So there's not even one physical part of you right now that has anything in common with the pictured person that you see from 10 years ago, but yet you're the same person. So how is it that an object maintains its self-identity when it's constantly shedding parts and gaining new parts and stuff like that? Another question that metaphysicians could talk about. But the metaphysical topic of inquiry that I've chosen for us, which is in our book, is the topic of the metaphysics of time. So I want us to consider and investigate the nature of time. What is time? What is the best current day theoretical understanding of time? And what is different between the modern day relativistic conception of time versus the older Newtonian paradigm that we were having with Newton's laws before Einstein. So we're going to try and get into this, and we're going to spend a few meetings and a few weeks really on this new topic of the philosophy of time. So time. Okay, time. Time is something that we're all familiar with. Oh, Ship of Theseus, very good reference, Leo. Yes, the Ship of Theseus, what you're referring to, I guess you know, is a metaphysical puzzle about a ship that is gradually replaced piece by piece with new pieces of wood. And the question is it the same ship after it has been 100% replaced? Or if it isn't, at what point did it cease to be the old Ship of Theseus and become a new one? So that kind of example, good, Leo, is on topic for questions about what it takes for something to maintain its identity across time. WandaVision, Jerry, I'm not sure if I catch your reference. You might have to give me a little bit more to work with there. I feel like I've heard of this, but it's a little bit obscure to me at the moment. But yeah, anyway, metaphysics of time, guys. What I was saying just before addressing Leo's comment is that we live with time. We're all familiar with time. We live our lives according to the clock. You guys know that you're here right now because you're appointed to be in class between 10 and 11:15 on Tuesdays and Thursdays. You know how old you are. You know how much time is left in a presidential term or how much time is left in a given day or hour or even your own life. So we all closely monitor time and we live our lives according to the passage of time, and we coordinate our schedules in time. Oh, okay, cool. They mentioned the Ship of Theseus on WandaVision. Now I have to look up that actual episode and see, but I digress. So what I was trying to say is just this. Time is a universal common thing that we all live with and we seem to understand in our daily lives. But the thing is, you'll learn that it's actually very difficult to consider it in depth, to go beneath the surface level and to ask tough philosophical and scientific questions about time. That is something that's actually quite deep, very trippy, a little mind-boggling, and it requires us to really get into some interesting, heavy philosophy and science. So we're going to start then with the analysis of Albert Einstein's work. And our first author on metaphysics of time is Albert Einstein. So here's today's author, Albert Einstein. And Einstein lived from 1879 until 1955. Okay. And I'm sure this is a household name. Doesn't really take a person with a huge academic background to have heard of Einstein. I think that this is probably worldwide recognized as perhaps the greatest ever physicist to live. He is, I would argue, kind of like the cultural meme of like the genius. You know, when you think of like a real genius, I mean, Einstein is almost like an adjective. Oh, nice move, Einstein. Like when you did something smart, or if someone's being sarcastic, you didn't do something so smart. The mustachioid figure of Einstein with the wild hair and the glasses, that is kind of like, I would say, the cultural archetype meme of like a genius scientist. So that's the image that pops up in most of our minds in the West when we think of someone really, really smart and brilliant. So he's a well-known cultural icon, but as well-known as his name is and his image, it's not true that a lot of people understand what he actually did or how he contributed to science and what his actual discoveries were. So we're going to try and open that discussion up and learn a little bit about how Einstein revolutionized the modern day understanding of time and space. What Einstein was able to show was that the older Newtonian way of thinking about space and time was wrong. What Newton had believed and what he had tried to argue for, and Newton's view of space and time was the dominant paradigm leading up till the early 20th century with Einstein. But under Newton's picture, time and space were totally separate from each other and independent from each other. What that meant was that they thought no matter how fast or slow an object is moving through space in terms of its velocity, that would have absolutely zero effect on the rate that time is passing. So Newton thought that time passes at a consistent, solid, steady rate, and that it is never ever capable of being changed or altered or affected by the motion of objects in terms of their velocity. So no matter how fast or slow an object is, time would pass at the same fixed constant rate, and that would never ever vary. But Einstein was able to show that this is not actually correct, that space and time are not independent and separate from each other, but rather that they're actually integrated into one common structure called space-time. And so what that implies is that how fast or how slow an object is moving through space actually does have an impact on the rate that time passes for that object relative to other objects which don't have the same state of motion or velocity. So it kind of shows us that time and space are connected, that how fast or slow objects are moving makes a difference to how fast or slow time is passing for them. And once you really come to understand the philosophical and scientific implications of this space-time conception, it's very powerful, it's very trippy, it's kind of almost mind-boggling, it's awe-inspiring. So we're going to try and get to those deeper understandings of the material. Okay, so, and again, what you'll see if you can get to that understanding is that it has very far-reaching and puzzling implications for our understanding of the universe and of ourselves as things within the universe. So let's go ahead and begin. The work of Einstein that we're reading, okay, so just a little background on him. He's so accomplished as a genius intellect because in his early 20s, after he graduated college, he was working as a patent officer, a patent clerk at the patent office in Germany, just looking at patent applications and approving them and evaluating them. And during that time, it's an office job, and he had enough free time on the side to continue pursuing studies in physics. So he was reading all of the latest cutting-edge stuff that was coming out of science journals and physics journals, mathematics journals, and he was developing his papers on the electrodynamics of moving bodies just as a kind of hobby horse pursuit on the side of his, patent office work. And then when he was in his early 20s, in 1906, he took these papers that he had been working on and published them, and then they became revolutionary, groundbreaking papers on the electrodynamics of moving bodies, achieved the Nobel Prize in physics, and it basically contains the special and the general theory of relativity. Now, those papers from 1906 that he did when he was in his young 20s that won the Nobel Prize, they're very important, but they're also very dense, technical, and a little intimidating for the average person that's not heavily trained in like physics and math. So he wanted then, 10 years later, he decided that he wanted to try and write a version of his ideas that would be more easily digestible to the general public so that there would be a more widespread base of people who understood his ideas. So in 1916, he wrote this book called Relativity. I think that's a really good book. I've read it and I've studied a little bit of it and I've written some material about it. But the book Relativity from 1916, again, that's just Einstein's attempt to bring these heady ideas down to earth a little bit so that the common man or woman could comprehend them a little bit better, and then his ideas would be more widely understood. So he tries to, again, write it to a more popular audience here, simplifying some of his explanations a bit so that more of us could understand it. And in our textbook, they took a section from this book and retitled it, and that's what we are assigned for today. So the retitled section of Relativity that we're reading in our text is just called Time and the Relativity of Simultaneity. Time and the Relativity of Simultaneity by Einstein. So, in this paper, the first thing he does is he asks us to consider a hypothetical scenario. So, the great philosopher, scientist, Einstein has a hypothetical for us to look at. This was just me getting started, showing you the name, the lifespan, the date of our publication, and the title in our book. So next, let's go into the essay itself. Okay, so Einstein starts with this hypothetical, and it's, at least at first, it's a somewhat deceptively simple sounding situation. So I want you to imagine this. Look at this line, and I want you to pretend that the line that you see is a railroad track. So this is like a railway. A train will travel along these tracks going from point A to point B, or, let's suppose that 2 lightning strikes happen on this railway track. So here's one of them, and here's another one. Now, let's mark the places where the two lightning strikes happen on the railway and label them with the letters A and B. So the lightning strike here to the left, we'll call it lightning strike A, and the lightning strike to the right, lightning strike B. Now I want you to make what, at least at first, sounds like a straightforward assumption. I want you to assume that these two lightning strikes happen simultaneously, okay? Let's say that they do happen simultaneously, the two lightning strikes. Sorry, just getting my phone here. Okay. And now the question that Einstein asks is this. Can you tell me what that means, that they happen simultaneously? Can you give a definition of simultaneous? And go ahead and try if you like, but what Einstein says, and this is, I think, true, is that it's not actually so easy to define this as it seems at first. Because any attempt to define the concept simultaneous becomes circular. A person will say, you'll try to define it and you'll say simultaneous means, you know, happening at the same time or not happening at different times. But that's circular for the term simultaneous, which just means same time as. So he says, try, if you will, to define simultaneous without just saying the same thing over again. You know, they're happening at the same time. In other words, what does it mean on a more deep level? In other words, for two things to happen at the same time? What does that mean? Can you say? I don't know. I mean, it's okay to try and have an awkward or incorrect attempt, because even the genius Einstein, as smart as they come, says it's actually really hard to define this when you think about it. What would you say if I asked you, what does it mean for the two things to happen simultaneously? Suppose that you're dealing with like a little 6-year-old and you say, whoa, look at those lightning strikes. They happen simultaneously. And they're like, what does that mean though? I don't know. I've never heard that word. What would you say? Oh, simultaneously. That just means that the blah, 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 what? What does it mean for two things to be simultaneous with each other? Any attempt to say? Let me hear. If you have anything, that'd be great. But if you don't have anything, I mean, I guess that's also reasonable, given that at the same time, synchronous, okay, I like that, Brandon, a little different. Kobe, something occurring at the same point in time as one another. Yes, all noble attempts and definitely good, but again, they really don't add much more to the concept same time as by just saying the same thing in slightly modified words. And so here's how Einstein says it, all right? He says, lightning has struck the rails on the railway embankment at two places A and B, distant from each other. I make the additional assertion that these two lightning flashes occur simultaneously. If I ask you whether there is meaning to that statement, you will answer my question, yes. But if I now approach you with the request to explain to me the meaning of the statement more precisely, you'll find after some consideration that the answer to this question is not so easy as it appears at first sight. Okay? And the next thing that Einstein talks about is this. He says, some people hearing me ask this question, what does it mean for the two events to be simultaneous? Some people becoming frustrated with the inability to give some kind of substantial answer may report back to Einstein, come on, who cares? Do I really need to define it? Because it's already well understood, you know? And he thinks some people might say that. They might say, kind of shrugging their shoulders, like, I don't know, I can't really define it, but it's clear enough. You know, if I say to somebody that right when I looked at my watch, at that exact moment, simultaneously, a car alarm went off, no one's going to stop me and say, wait, hold on, I didn't follow that last part. What did you mean simultaneously? You lost me on that. Like, people will be able to understand you, will be able to communicate easily, will use the word, and no one's going to ever raise a question about how it's to be interpreted. So isn't it fine if we just operate without a formal definition? Einstein says to that answer, no, I won't let you have that, because he says if you're a physicist, you have to have concepts that are defined with precision. Otherwise, you may be using a word that does not actually have any kind of clear meaning. So here's the way he said it. He says, after some time, perhaps the following answer would occur to you. Quote, and he's quoting an imagined response. The meaning of the statement is clear by itself, and it needs no further explanation. Of course, it would require some consideration if I was to be commissioned to determine by observation whether in the actual case the two events took place simultaneously or not. And Einstein says, I cannot be satisfied with this answer for the following reason.
Supposing that as a result of ingenious considerations, a meteorologist was to discover that the lightning must always strike the places A and B simultaneously, then we would be faced with the task of testing whether or not this theoretical result conforms to the reality. We encounter the same difficulty with all physical statements in which the conception simultaneous plays a part. The concept does not exist for the physicist until he has the possibility of discovering whether or not it is fulfilled in an actual case. We therefore require a definition of simultaneity such that this definition supplies us with the method by means of which, in the present case, we can decide by experiment whether or not both the lightning strikes occur simultaneously. As long as this requirement is not satisfied, I am allowing myself to be deceived as a physicist, and even if I am not a physicist, when I imagine that I am able to attach a meaning to the statement of simultaneity. And I would ask the reader not to proceed any farther until they're fully convinced on this point. So what he says here is, in the purposes of science, we have to have our concepts clearly defined, and we have to be able, therefore, to define the idea of simultaneity with such definiteness that we could actually perform a test to determine whether or not the two events are simultaneous or not. Essentially, he's saying if we don't know how to test for this question, whether they're simultaneous, then we may be using a word that does not have any kind of clear definition. It may be an undefined concept, so a word without like a real meaning. So he insists, therefore, that we supply the means by which we could conduct an experiment and test whether these two things are simultaneous. And he says, until you agree with me that we need to be able to perform such a test to understand what we're saying when we say simultaneous, then don't read on any further. So he says to the reader, stop right there until you can agree that we need to be able to form a test for the question of whether they're simultaneous. Okay, so he says, what's the test basically then? What would be the experiment or test that could be conducted to determine whether those are simultaneous? So Einstein next says, all right, I got you. Here's what the test will be. Let me propose a test. So the test by means of which we could determine whether those two lightning strikes happen at the same time. Here will be the idea. Let us measure the distance between the 2 points A and B, right? Now, since that's a measurable distance, it could be considered a line segment. So like the line segment AB, if you recall studies in geometry. Now, with respect to lines, there's always a midpoint, right? The midpoint of a line is the point that cuts the line in half. So it bisects the line. It's equidistant from the one point at the beginning of the line to the other point at the terminal point, the end of the line. So let's measure the distance between A and B and designate the midpoint M. M labeled for the midpoint here. And let's place an observer standing still at the midpoint. So I just draw the stick figure character who's positioned at M, and they're at M, which is equally far away from A and from B. That's the midpoint. Now, next thing is this. We need to make sure that our observer who's at the midpoint is able to view both A and B in the same visual field, like in the same frame of his vision. I'm using this term frame of vision to refer to like what you can see in one visual field without having to move your head around and look somewhere else. So like right now, if you're looking at the screen, your visual frame encompasses the device that you're watching this on, and then in your peripheral vision around it, I guess, like some of the things in your room where you're at. Now, all I'm telling you is Einstein says we have to make sure that this guy is far back enough from the railway that he can see A and B in one visual field without having to like look around left and right. Now, do you guys understand why it's important for him to be able to see the two things in one field of vision? Because he needs to be able to see the 2 points in space to be able to judge whether they're happening at once or not. Because if he was only able to look at one at a time, like say he was up close to B and he sees lightning go off, but he's so close to it that he can't even look at A yet, so he has to then turn his head towards A. If that was the case, then he would not be in position to even make the judgment as to whether they were simultaneous. Because seeing one, quickly looking over here and seeing the other, it could have been that because it takes a short amount of time for your eyes to shift their position, that in the meantime, while you were turning your head is when the second one started happening after the first. So there would be no way for you to tell if they're simultaneous or not unless what? Unless you could see both at once. So we make sure that he's standing far back enough from A and B that they're both placed in his visual field. Or, and this is another way of doing it, Einstein says if the person is too close up, then we will simply supply him with a set of angled mirrors inclined at 90-degree angles, and then the mirrors will supply him with the means by which he can view the 2 points in space.
This will either allow him to use mirrors if he's too close, or get him far back enough so that he can look at A and B at once. Okay, now, if this guy who's standing at the midpoint M, standing still, and can view A and B in one field of vision, if he observes the two events happening in one and the same visual perception at the same time, then relative to him, we can say the two events are simultaneous, but we have to add another stipulation. Okay, so quick question, guys. Let's think openly about this. How does vision work? How is it that physically, like, vision does its thing? Right now, how are you able to see this screen? It's not magic. It's not like you just say, hey, magic eyes. They just see stuff. How does it work, though? How is it that you see anything? What is the mechanism of vision, and how does it actually, like, just a little bit of a detailed description, the nuts and bolts of it. How is it that the eye works? Right now, you're using your eyes. So how is that happening? Okay, good. That's right, Kobe. So light travels, and it reflects off of the surface of the object, and then it strikes your retina, and your brain processes the visual information contained in the light. Okay, so sensory organs interpret the light that reflects off of the object's surface and gives you the vision of it. To understand this even more perhaps clearly, if you close your eyes, right? Close your eyes for a minute. Do you see how everything's black and your field of vision is darkened and just blacked out? Why is it that when your eyes are closed, you do not see anything? Well, it's, I hope, perfectly clear, right? It's because with the eyes closed, you're blocking incoming light rays from striking the eyeball, from striking the retina. The shades of flesh that your eyelids are cover the eyes physically, so incoming light cannot strike it, and therefore you don't see anything. With the eyes open, the light that reflects off of a surface object in the distance is then collected by the eye and perceived as vision. So anyway, whenever you look at things, you're actually seeing them because of the effect of light, which has traveled off the surface of the object and bounced back over to your eye. It happens very quickly because light moves at a certain speed, but it is a finite speed. So now, for this experimental setup to verify that the two events were simultaneous, we have to make this last assumption, which is that the speed of light is always constant and fixed, meaning that the speed of light remains the same speed from each direction to every other. In other words, the direction of light from A to M is traveling at the same speed as the speed of light from B to M. We must hold this assumption because if light moved at variable speeds, like say if light moved faster from A to M and slower from B to M, then even if the two light signals reached M at the same moment, we could not therefore deduce that they had departed from their origin points at the same time. Only on the supposition that light moves at the same speed will the common receipt of the light signals at M at the same point imply that since they traveled the same distance at the same velocity, that they left at the same time. Let me give you an example about that to sort of reinforce what I'm saying. Take this as an analogy. Suppose that A and B are not light rays that travel to M where there is an observer positioned, but that A and B are runners running a foot race, and there's a set designated distance, like 5 kilometers, from A to M and from B to M. So this is like the starting line, and this is the finish line. Now, tell me this. Suppose that A is twice as fast of a runner as B is. So whatever speed B can run, A runs 2 times that amount. So if the speed of B is x, the speed of A is 2x. Okay? Now suppose that A and B are the 2 runners, they've entered the race. A is twice as fast as B, but they meet at the finish line at the exact same time. They have a photo finish where they both cross the line at the same moment. Now if they both finish at the same time, but A is twice as fast at running, then who left first? Can you answer that? Suppose A is twice as fast as B. Suppose they have a set distance which they cover and they reach the end at the same moment. If A is twice as fast as B, but they reach the finish line at the same time, then who left first? B left first, correct. That would be like the tortoise and the hare scenario, where B is a twice as slow runner, so A gives him a head start. And it's like this. Okay, start. He's going, going, going. He gets about halfway, and now this guy who's twice as fast gets started, and then they meet at the finish line, okay? So now, if A and B move at different speeds, then arriving to M at the same time would not imply that they left at the same time. So we must therefore assume that light is not like these 2 different runners, but that light is the same speed from everywhere to everywhere else. If we do assume that, though, then we can use the experimental setup here to verify that the events were simultaneous with reference to him. Because here's what will be held fixed.
The distance from A to M is equal to the distance from B to M. The two light signals arrive to M at the same moment, and if they are traveling the same speed, having covered the same distance, and reaching the same terminal point at the same time, then they must therefore have departed from their respective origins at the same time as well. So on the assumption that light moves at a constant speed, this midpoint observer will see the two events happening simultaneously if he's interposed between them and they reach him at the same moment. Now let me read Einstein as he puts it. He says, after thinking the matter over for some time, you offer the following suggestion with which to test simultaneity. By measuring the rails, the line AB will be measured up, and an observer placed at the midpoint M of the distance AB. This observer will be supplied with an arrangement, perhaps mirrors if necessary, which allows him visually to observe both places A and B at once. Now, if the observer perceives the two flashes of lightning at the same time from this position, then they are simultaneous relative to him. But then he adds this point about how we have to stipulate that light is always at the same velocity. So he says, I'm very pleased with this suggestion, but for all that, I cannot regard the matter as quite settled because I feel constrained to raise the following objection. The definition would certainly be right if only I know that the light by means of which the observer at M perceives the lightning flashes travels along the length A to M with the same velocity as along the length B to M. And then he says, this is a stipulation that I can make of my own free will to arrive at the definition of simultaneity. So there we now have this definition of simultaneity given in terms of the transmission of light rays off of an object's surface to the visual system of a standard perceiver. In the case given here, what it means for two events to be simultaneous then is for the light rays to arrive to the observer at the same moment that they're doing the observation of the two things. So in this sense, we can define any two events as simultaneous if, again, the observer who observes the two events has the incoming light signals arrive to him at the same time. So then consider what clocks are. Clocks are just ways that we can coordinate our movement and actions in space by having a reliable measurement instrument where we can then assign events to coordinates that are shown on the clock face. So for example, if this was a face-to-face class meeting and the schedule was meet every Tuesday, Thursday, 10 to 11:15, say there was like room 100 of the humanities building. What it means to say be there at 10 a.m. on Tuesday is to, in other words, according to this analysis, make these two things simultaneous. The observation of the pointer hands of the clock showing the time indication of 10 a.m. on that date, make that observed simultaneously with you taking a seat in the classroom. So if those two things will be seen by the observer at the same time, then we will say of them that they're simultaneous. That's what it means, in other words, to say class starts at 10. Now, this is already kind of weird and interesting because we're talking about simultaneousness with reference to the receipt of incoming light rays from two distant events. But it's about to get even much, much weirder and even trippier because we're going to show next that according to this analysis of simultaneity, that simultaneity is not absolute, but rather it is relative. So whether two events happen at the same time is not an absolute fact. It's relative to the condition of the observer and their state of motion, which is very, very deep and strange. But I'll explain it. So now let's continue. To get to that next part of the results, we have to add a second observer to the scene. Okay, so this guy's still here, but in addition to him, let's suppose there's another observer, and the other observer's got a different state of motion. So the second observer's on a train that's actually moving along the railway from left to right with a certain constant velocity v. So this letter v just stands for the velocity of the train, whatever it is. Here inside the train, you've got this person, an observer. Now, the observer who's on the moving train shares the velocity of the moving train, and so in science we say that he has that as his reference frame. He observes all events relatively to the moving frame of reference that the train is. Just like when you're driving in a car, you know, you look at yourself in the car and you're like, well, I'm sitting still, but you're moving around very fast. A stationary observer outside of the car would see you whizzing past them and would see you as a fast-moving object. But relative to the car, your frame of reference as you flip a coin is that it's just going straight up and down. Relative to a person standing outside seeing you drive past while flipping the coin, they see the coin just going like straight forward vertically or sort of horizontally. So when we have different states of motion, one at rest, one in motion, one at a different velocity than another, we say we have different reference frames. So there's one reference frame described by the motionless observer at M, and there's a different frame of reference, which is the observer's frame of reference from the train given its velocity. Now, from the train, he observes all events in reference to the moving train. So every event that happens on the embankment happens at a particular point along the moving train. So as he continues his path of travel from left to right along this railway, he's going to traverse the midpoint between A and B. And to designate the midpoint seen from the train observer's position, let's label it M prime. Prime just to indicate that it's the same midpoint, but it's seen from the train rather than the stationary observer. Okay. Now, the guy who's on the moving train has this velocity v, and it's carrying him towards B and away from A. I want you to suppose that as he moves forward, he traverses the midpoint M prime, and as he surpasses this midpoint, at that exact split second, he's aligned along this plane with the other guy at M, and he does his observation while the first individual standing still does his own. Okay, from the stationary observer's position, we already said that he sees the two events happening simultaneously because the light rays arrive to him at the same time, given that he's equidistant between the two sources of light and he's standing still. But for the second observer, who's carried to the right with velocity v as he passes the midpoint, what do you think will be the order of experience for the second observer? If he were to traverse this midpoint at the exact moment that the first guy does his observation, which of the two events do you think that he would see first, or would they be simultaneous? For the guy in the train, question. If he does an observation of A and B, the 2 points in space, as he bypasses midpoint M prime with velocity v, will he see A and B happening simultaneously or not? What do you think is my answer? So the first guy who stands still sees them as simultaneous. The second guy moving towards the right, passing the midpoint as he does so, what do you think would be his case? Would he see them as happening simultaneously or not? The second observer who's on that train. Yeah, so Brandon, you say his velocity causes the light to hit at different times. Correct. His velocity carrying him closer to B, further from A, is going to dictate that which one is seen as happening first. You're right, Brandon, yes. But now I have a follow-up question. They won't be simultaneous for the moving train observer. Which one will happen first according to his experience? Since they're not simultaneous, one happens before the other. They're out of sequence. So which one would be first, do you think? Based on his direction of travel and velocity as he passes the midpoint. Anyone can tell me. So we've established it's going to be that he will see whichever one he is closer to first. Correct. And so naming, that means it's B that he sees happening first. Now, sometimes when I teach this material, some students have one fundamental misunderstanding that I don't want you to have. Sometimes students are like, okay, well, he sees B first because A is behind him and he can't look at it because it's back behind his head. No. Okay, he's got the same kind of viewing setup that the other guy has. If he has a mirror here that's directed back towards A, then he can look at that as he's looking ahead towards wherever B is at. So there's no issue with like head turning or not being far away enough or anything like that. It's merely the amount of time that it takes the light rays to catch his visual system because he's a moving target, running away from A, getting farther from it, and hastening closer towards B. So unlike in the first person's case, the light rays have equally distant path to travel. The distance from A to M is equal to the distance of B to M. And since they move at the same velocity, they reach M at the same time. But in the case of this other guy whose velocity is carrying him closer to B and away from A, since he passes the midpoint M prime just as he does his observation, he's extending the gap between himself and A and decreasing the gap between himself and B. So now we have asymmetrical distances for the light rays to travel to reach his visual system. It's not a 50-50 length where they're both the same. A has farther to go to reach him as he's running away from the midpoint, and B has less distance to go to reach him as he's closing that gap. So with the same velocity and two different distances, one longer than the other, they cannot possibly reach his visual system at the same time. In other words, the light ray from the one that is closer to him, which he's moving towards, will hit him first, so he'll see B, and then subsequent to that, A afterwards. How trippy is that? That's very trippy and weird, because you have to fully process exactly what's been claimed and what has been implied by these results. Question then. So it's a trick question, guys. So understand that before I even say anything else. I'm asking you a trick question, so you got to give a tricky answer. Here's the trick question. Considering these lightning bolts, A and B, are they simultaneous or not? Are they or are they not? What do you think is the answer? Trick answer. But I think you can get it. It sounds like a simple yes or no question. Are they simultaneous or are they not simultaneous? The two lightning bolts, based on what we've now studied and learned from Einstein. There you go, Kobe, correct. It does depend on your frame of reference. What's that word? The word is that it is relative. It's relative. It's relative. So in one person's condition, the two events are simultaneous to the motionless observer at M. To another person's frame of reference, given their state of velocity, in reference and in comparison to the other person who's standing still, it is B happening first and then A. So in one person's case, they're simultaneous, and in the other person's case, they're not. Now, Jerry, I understand some people might have been sitting there thinking, well, is that really true, though? Isn't it just actually simultaneous, and the other guy's just seeing something that's like an illusion because he's moving through space and the other guy's standing still? That's not correct either, so disabuse yourself of that notion. It's not that there's one person who gets the real observation, and then the other person sees a distortion of reality. Both observers have just as much equal claim to be the correct observer of the events. You may think that because he's so-called motionless, that he has the correct objective observer's viewpoint. But nothing in this universe is ever at a true state of rest. If you guys understand, everything's at motion. The only time you call something at rest is when relative to something else, it doesn't have the same state of velocity. If you're sitting still right now and you think you're motionless, I have news for you. You're on the surface of the planet Earth, which is hurtling through space at an extreme rate of velocity as we orbit the sun. And so we can only claim of ourselves that we're at rest if we compare our frame of reference to something else that does not share the same current state of velocity. So just as much as this guy, he's in motion too, but we define him as having rest given the frame of reference that we're comparing him with. So either one can say, I saw it simultaneous, or I saw it not simultaneous, and neither one can be claimed as being the correct or incorrect party. Brandon, so if the lightning bolts were to strike two people, one at A and one at B, which one would die first if it is relative to the observer? It would be relative to the observer. So in one observer's case, they die simultaneously, and in another observer's case, it would be one before the other, and there's no objective fact, Brandon. How weird is that? You might think that, well, okay, because it's death, there has to be a fact. But even that, no. It's like Schrodinger's cat. In the case where he's going to survive the photon beam passing through the magnetic plate, in the case where he's going to die, physics tells us that if you take the no-collapse theory of quantum physics to be true, then both events happen in different vectors of quantum reality. But anyway, let me make it even weirder for you, okay, Brandon? You want to get even trippier with this? Take a third possible observer to the scene, all right? And suppose they're on another train that's moving in the opposite direction of travel, from right to left, with velocity v. And in this train, we have an observer, and when they pass the midpoint double prime, all three of these guys are in, for a split second, in perfect alignment. So imagine we had a video playing through that recorded the sequence of events here. And the video is playing, and then pause the video. At the video pause point, all three observers are aligned along the plane of the midpoint. But when you hit play again, this observer is carried to the right with velocity v. This observer is carried to the left with velocity v, and he stays at m. And so what would be the experience of the third observer in this description of events? It's the same kind of phenomenon, just in the opposite direction of travel. So for the third observer up top, m double prime, he will see which event first in his order of experience. Can you tell me that one, if you're following? The third observer. Yes, A would strike first, and then subsequent to that, it would be B, for the exact same reason, that as he closes the gap between the emitted light ray from A and extends the gap between himself and the emitted light ray from B, they will strike his visual system at two different moments in time, not the same moment, and therefore he would see them happening in the reverse order. So now the strangest weird thing is this, okay? What a strange set of facts we are given. Here's the facts. A and B, two lightning strikes, are simultaneous according to one account. In another account, they're not simultaneous because first it is B and then it is A. And in a third observer's possible order, they're not simultaneous because it is A and then B. So with respect to A and B, we have three apparently inconsistent statements. They're happening at the same time. B is first, also A is first. If these three are all equally valid descriptions of reality, then some of the most deep and far-reaching implications of the theory of relativity is that we have to consider that all the moments and events of space-time are equally real. So there's not a single present relative to which the past and future are before and after. What this implies, what this simple thought experiment implies, is that there's no such thing as any linear ordering in objective reality of the sequence of events in space and time. Now that's weird, because you're sitting here right now and you're looking at the future and you're thinking, well, those things in the future, like me getting older, graduating college, starting a family, starting a business, retiring, whatever, traveling the world and having all those new experiences that you haven't had yet. You think of that as something that's completely indefinite because it hasn't happened yet, and whether it happens or not is completely contingent. But according to the space-time theory, no. What's in your future, relatively speaking, could be perceived by another given observer in the universe as an event that's already happened in the past. And since, from the relative point of view of this observer, B is present and A is future, but in another observer's experience, A is present and B is future, that means that there's no objective linear ordering to what you would call past, present, and future. So that implies that you have to conceive of all the events, inclusive of the full past, present, and future, as all being equally real and not happening in a sequence or in an order. So this is what some call the block universe or four-dimensionalist view of reality. And this is the current consensus view of modern day theoretical physics and science. So a lot of things that we study in this class are, philosophical, and that's great. But here in this one case, it's both philosophical but also grounded in actual empirical science. There have been detailed physical and empirical verification for Einstein's theories. So as strange as these heady thoughts are, they seem to be the consensus view if you actually go out into the field and see what scientists of space and time are saying today. But it's so strange, right? Because it starts to tear away at your whole concept of having human free will. According to the space-time conception, all the moments of your entire future course of life are fully set forth because they all exist in the big block universe system, which contains all the moments of space-time. So in this way of looking at space and time is integrated with space, and it's just a big container containing all the moments. It's not something that unfolds in an order. So there's no coming into being, there's no passing out of being. All the moments equally exist, and they're co-located in the big manifold of space-time. Then the mystery to explain is why it is that our consciousness seems to reveal the experiences in a set order if they all are equally real. And it's very strange stuff. Here's the words of Einstein on the point, okay? So he says, are two events, two strokes of lightning A and B, which are simultaneous with reference to the railway embankment, also simultaneous relatively to the train? I will show directly that the answer must be negative, no. When we say that the lightning strikes A and B are simultaneous with respect to the embankment, we mean this. The rays of light emitted at the places A and B, where the lightning occurs, meet each other at the midpoint M of the length A to B of the embankment. But the events A and B also correspond to positions A and B on the train. Let M prime be the midpoint of the distance between A and B on the traveling train. Just when the flashes of lightning occur, this point M prime coincides with the point M, okay? But it moves towards the right in the direction in the diagram with the velocity v of the train. If an observer sitting in position M prime in the train did not possess velocity, like if they just stayed at rest here, then they would remain permanently at M, and the light rays emitted by the flashes of A and B would reach them simultaneously. But in reality, he is hastening towards the beam of light coming from B, while he is riding on ahead of the beam of light coming from A. Therefore, the observer will see the beam of light emitted from B earlier than he will see the light emitted from A. Observers who take the railway train as their reference body must therefore come to the conclusion that the lightning flash B takes place earlier than A, and therefore we arrive at the important result. Events which are simultaneous with respect to the embankment are not simultaneous with respect to the train, and vice versa. Every reference body has its own particular time. Unless we are told the reference body to which the statement of time refers, then there's no meaning in a statement of the time of an event. So, Newton would have thought that given a sequence of events, there's just one objective fact about what order they play out in. They cannot both be simultaneous and also non-simultaneous, or if they're not simultaneous, happen in one order and then in the reverse order. But what Einstein shows is that all of these things are relativistic. And so the sequence of events in time, or even the duration of events in time, will vary depending on one frame of reference's state of velocity in comparison to another frame of reference's state of motion. Brandon, if you're above ground, does that change things too, since you are further from the point of impact, like viewing from a plane? Yes, Brandon, it would. Objects and events observed from space as non-simultaneous may appear simultaneous from a position on the Earth. And it all depends on the relative distance that the observer has from the observed events, the speed of light, and the amount of time that it takes them to reach the person's visual system. So yes, it's a possibility, but I would probably need a more specific example to make a more precise diagnosis of the case. But yes, that kind of general thing is possible, to have those differences depending on the condition of the viewer relative to another viewer and their differing states of motion or rest. The buffer wheel, Janice? I don't know. Can anybody confirm or deny the case of a buffer? Is there buffering issues right now? Janice, have you tried hitting the live button on the lower left corner of the viewing box if you're watching on your handheld device? If not, then you can also try clicking that if you're watching it on a desktop or laptop, and that should bring you back to live. Sometimes if you go out of the live stream and come back, you'll notice that it's playing a previous point of the lecture, and you may have to then hit refresh or the live button. So I think maybe, Janice, it may be more on your end in this one case, but not to worry, the video is archived and it's going to show up later. I'm not 100% sure, since I'm speaking to you live, if you're watching a previously recorded part, but just do your best. I think it'll be okay. So let me just add a few more thoughts here at the end. When you look out in the night sky, or anywhere really, because of what we are learning about how the transmission of light rays leads to the phenomenon of vision, you do always see things on a slight delay. Isn't that kind of interesting? So even when you're looking at the sun, which you shouldn't look at directly, but to see the light coming from the sun, it takes about 8 minutes for the light to have traveled 93 million miles from the sun to the Earth. Now, the speed of light is the fastest physical speed achievable in the universe, which is 300,000 kilometers per second, or in the English and American system, 186,000 miles per second. That's so fast, right? We're not saying 186,000 miles per hour, which would be incredibly fast, but literally 186,000 miles every second. So that is how fast light travels. And light is the ultimate conveyor of all information in the universe. So because 93 million miles divided by 186,000 miles per second is about 9 or 8 minutes, that's how long it takes from light from the sun to reach the planet Earth. And if you're looking at stars, let's say through like the Hubble telescope that are far deep in interstellar space, then in many cases you're seeing those stars as they were millions or even billions of years ago. If it takes 1 million light years for the light to reach us, then that star might even have blown up in the time period in between when the light was emitted from the object to when it's finally collected by our telescopes and eyes here on Earth. So, and let me get your question, Kobe. If someone super far away from Earth looked at Earth through a telescope, would they see a different period of time? Kobe, very much so. I was about to make this point. So, but here's the weirdest relativistic thing about that. If you had a telescope pointed off into space and you're looking at like the deep field and you're seeing galaxy clusters and stuff that are billions of years old, you look at that and from our position on Earth, you say that is the past. We're looking at the distant past of the early universe by seeing that stuff that's been carried through so much time and space by light. But imagine that there was an observer in that point of the cosmos that had telescopes pointed in our direction towards the Milky Way. And they would be looking at us. And from their vantage point on the other end of this divide, they would look at those images beamed to them through the telescope, and they would think, wow, that is the past. So from our direction looking at them, we say that's the past. From their direction looking at us, they say that is the past. So what's the future, what's the past, and what's the present? Once again, you start to see that it all falls apart, and it's just all there. All the objects are just equally existing and real, and there's no objective sense in which one is really in the future and one is really in the past. So if someone was super far away and then looked at Earth through a telescope, they would be seeing a different period of time. But the interesting, weird thing about it, Kobe, is they wouldn't be watching like a video, okay? They'd be watching live images of it, just how long it takes the light to reach them. So the whole idea then of what's happening now and what's happening in the past itself starts to disintegrate and fall apart. It's kind of mind-bending, isn't it? You start to think about how just all the events equally exist, and it's only the relativistic position and speed of observers that makes us think there's any such thing as a sequence at all. Heady stuff, weird stuff, but interesting to digest and think about. It's the intersection of science and philosophy. And, you know, in our class, we study a lot of topics in philosophy that are ancient. You know, we studied the arguments for the existence of God that have been debated for literally thousands of years. But now we're studying some philosophical topics that are just for us, just for people living right now at the tail end of history, because there was no such thing as the theory of relativity. There was no such thing as even Newton prior to the early modern era. So it's not our ancient ancestors, ancient Greeks, people living 1,000 years ago in the time of Anselm, or even 500 years ago in the time of Descartes. None of these people were able to consider these heady topics that we're looking at right now. So I think it's kind of a unique privilege of being modern day students of science and philosophy. Brandon, since the universe is expanding and getting further away from everything, is time regressing then as we see things far away? Yeah, there is the expansion of all matter outwards, which is measurable. And there's some scientific questions about what's fueling this expansion, because we're not sure which laws of physics are responsible for it, or will it ever contract again. Some people harbor the position that perhaps the universe is like a big kind of expanding and contracting system that goes in cycles, and the Big Bang is just the most current cycle of this expansion and then contraction phase. But if space and time are woven together into one common structure, then anything having to do with the growing sphere of matter in space would also, I think, have to do with time. But that's something I think that I'll have to double check on in the theoretical physics to give you a more clear answer about. Yeah, and so I wanted to also speak about a couple of other implications of Einstein's work for the concept of what's called time dilation and the twins paradox. So I know we have about 9 minutes left. Maybe that's enough time for me to at least set up the beginning of the concept of time dilation and the light clock. And when we close today, wherever we're at, we'll pick up from there at the beginning on the next meeting Thursday. So one implication of Einstein's work and the theory of relativity is that how fast or slow an object is moving can change the amount of time that passes for that object relative to others, which is a very interesting and surprising result. So to know how this works, let's look at what's called a light clock. I want you to imagine that these two lines represent two planes of glass that are mirrored on their surface. So a mirrored glass is a reflective surface. As you guys know, when you look in a mirror, you're able to see yourself. Why? Because light reflects off of your body, then it strikes the mirrored surface, which reflects that light back, and it perfectly captures the image of the thing that stands before the mirror, which is bathed in light. Now, let's take a photon beam, a little particle of light, and we're going to accelerate this photon up to the top plate of the dual plate light clock. Since this is a reflective surface, it's going to just shoot the same photon beam down to the other plate. And because this is itself a reflective surface, it fires it back up. And that means that now we have this kind of perpetually bouncing photon beam in between the two planes of light. Since light moves at a constant fixed speed, let's use the consistency of this beam of light as a time measurement device. So I just want you to visualize in the mind this little beam of light completing one cycle of touching the top and bottom every second. So it then becomes effectively a clock device. 1, 2, 3, 4. So it just keeps bouncing up and down like that, using the reflective surface and the excited photon beam. Now, I want you to suppose that we have two of these light clocks, two of them, right? Here's number 1 and here's number 2. And we have an observer here that's just standing by, observing both. Now, the first clock, this one, let's say we leave it motionless. So, I mean, it's counting seconds, but it's standing still. It's not accelerated with any velocity. It's motionless with this motionless observer who's standing with it. But now let's take the top light clock, and we're going to accelerate it very, very fast to the right with a high velocity v, maybe even approaching the speed of light. Okay, so this light clock up here, I want to put it to the left so I have more room to show the next things, but it's going to be accelerated fast to the right with a huge velocity v. Now these two light clocks initially were perfectly synchronized. Let's say they even came off the assembly line of the factory at the exact same moment and then started counting seconds together. So they're perfectly in sync. For every second counted by one, the other one counts a second. So they're moving perfectly in tandem, in synchronicity with each other. But now we're going to leave this one at a state of rest. And as I said, relative to it, we're going to accelerate the other one very fast to the right. Now, the path of travel that the photon beam will appear to take to this observer regarding the motionless light clock is going to be a simple vertical path, up and down. Just straight up and down like a line, because it bounces up and it's straight down and it's standing still and he's standing still. But what if, okay, we take the other light clock here and accelerate it fast to the right while this one keeps sitting still, bouncing straight up and down? Question, guys. Try and visualize this in your mind. What do you think would happen to the angle of approach of the photon as it makes its journey from the top plate to the bottom plate once it's accelerated relative to this guy who keeps standing still? So he stays put, top light clock is accelerated to the right. Question, will the angle of approach of the photon still appear to be a straight up vertical line? Or if not, how will it change? The angle would change, Kobe, correct. In what way do you think visually it would change? What would be the new trajectory of approach? You say diagonal line. Correct, Kobe, exactly. It will appear from the stationary observer's viewpoint that the line now traced by the photon is a diagonal. So it's going to now look like this. Up, down, up, down. And it's going to be a more gradual diagonal approach the faster that the light clock has been accelerated. And this is a familiar phenomenon that can also be seen in the case of what's called the Doppler effect, which has to do with sound waves. So light has both wave-like and particle-like properties. And the wave-like properties of light account for this phenomena where you would see it as though approaching at a more gradual angle as it's accelerated faster. When you're standing still and a car drives past you with its horn blaring, you actually hear the pitch of the horn change in its tone. As it gets closer to you, the fast-moving car, while you're standing still, the pitch goes up. I'm not just talking about the volume. I'm talking about the pitch, so it sounds like a higher pitched frequency. And the reason for that is because as the object which is emitting the horn's noise is closer to your ear, the sound waves get more spiky and scrunched up because the gap between you and the object emitting the sound is shorter. And now as it accelerates away from you, the same kind of sound wave gets more, the amplitude and trough of it is more stretched out and gradual, producing a lower tone. And so that's why you, the stationary observer, hear this auditory phenomenon as it goes past. Now the driver in the car just hears because they share its state of motion, so they don't have that variability that happens from the space changing between you and the object that emits the sound. So in the same way, therefore, when it's a photon with its wave-like properties as a light ray, the stationary observer will see a more gradual angle of approach depending on how fast that fast-moving light clock has been accelerated. Therefore, question. Suppose then that we've allowed the top light clock that's moving so quick to continue going very fast, orbiting the planet many, many times. Finally, then we return it to a state of rest with its twin, its other counterpart light clock. Having now returned to the state of rest, which of these two light clocks do you think will have counted off more seconds? The one that had the straight vertical approach, or the one that had the more gradual diagonal approach because of its extra velocity? Which of the two would have had counted more seconds now that they have been reunited? One of them has ticked off more seconds than the other one, I have to tell you that. And which one? The vertical one. So in other words, the motionless light clock that stayed at rest has ticked off more seconds than the other one. And there's a simple physical reason. Because the length that each cycle takes to complete is a shorter amount of length because this is a more extended line given the fact that it's a more gradual diagonal path. So the motionless and stationary clock has counted more seconds than the one that's moving fast. This is very strange because what it means is that they are not the same age anymore, these two light clocks. They came out of the assembly line at the same time, but now one is more seconds older than the other one. Now you might be thinking, well, objectively they're the same age. It's just one has counted more seconds than the other, but no, that's the different rate of time passing for the two objects. Now, if we had two observers, one of them on the light clock traveling with it, then that other person will have aged less than the person here who's remained at rest. So this opens up another big implication of Einstein's work, which is the time dilation phenomenon. And basically, here's the rule. When you're a fast-moving object through space with your velocity, then you're passing through time slower than other objects which are comparatively, if you're moving through the universe really quick, if you're accelerating close to the speed of light, you'd be passing through time much slower than other people who don't share that state of motion. And this is why, like in the film Interstellar, I don't know if any of you guys have seen that or know about it, but there's a lot of science fiction films which explore these physical theories in their plots. And one of the climactic scenes of the movie, sorry if it's a spoiler to anyone, but Matthew McConaughey is like a character in the film who travels on these interstellar space missions, going around in space, going very fast. After he returns home from one of these missions, he comes home and his daughter is older than him, and she's dying on her deathbed because she's an old senior citizen, and he's kind of comforting her. Now, you would look at that and you would think, this is not possible. If you have a kid, you're always going to be older than your kid. There's no way they can like leapfrog you in age. But it is an implication of these theories that if we had the means by which to accelerate someone that much faster than a counterpart of theirs, then they would be passing through time so much slower than the other person that depending on how fast they were going and for how long, we could achieve this effect of like, you know, you have a kid that ends up being older than you. For you, like 5 years or 5 months in the space shuttle going at that speed is like 10 years, 15 years, 20 years for the people back at home, for the same reasons as advanced here in the case of the light clock. Now, the person who's on the moving light clock, of course, doesn't see any diagonal anything because they're moving with it. So to the observer stationary here, he would see the person in the light clock, see the diagonal, but the person on it would still be moving with it, seeing it going up and down, like as if you're driving in a car and you're flipping a coin. You just see it go straight up and down. But for a person outside watching it, if they were to track the actual trajectory of the coin, they would see that it goes up at a trajectory of a diagonal because the car keeps accelerating forward as the coin starts to take its ascent. So there's just these two different reference frames, and it gives rise to two different experiences of time. How strange is that? Well, there's more to say about it, and we're going to add to this on Thursday, but we're out of time for now, I guess. So let me know that everything's good, and if so, we'll resume on Thursday and be back in at 10 a.m. So what's up? Are we all good to go? Just let me know. Okay, perfect. Thanks, Mia. Thank you so much, and everybody else. Appreciate your continued attendance and focus. Do read the materials, okay? I mean, I'm trying to lecture and make it as clear as possible, but you'll do yourself a big favor by backing that up with at least skimming the articles and touching base with what they say as well. All right, guys. Yeah, make sure to give yourself your best chance to do well in the class by reading the material and following up on it. Don't just cram in stuff at the end. That, I think, sometimes produces problems with tests, but we'll get to that later. Okay, thanks again, everyone, and have a great day, and I'll see you back on Thursday. Okay, bye-bye.